My name is Jose Pablo Chavez. I am co-leading ISGAN Virtual Learning together with Mateo Tronche. We are both from Comillas University. And let me introduce a little bit of ISGAN, which is the International Smart Grid Action Network. It's a technological collaboration platform with the International Energy Agency, together with the Clean Energy Ministerial, which was formally established in 2011. It can create a strategic platform to support high-level government attention and action to accelerate the deployment and development of smart grids and cleaner electricity grids all around the world. So currently, ISGAN consists of 28 contracting parties. The countries that the flags you see on the screen, and they nominate the executive committee that headed by the Presidium and assisted by two different co-secretariats, one from the Austrian Institute of Technology and then from KSGI from Korea. So ISGAN vision is to accelerate progress and key aspects of smart grid policy, technology, investments, and voluntary participation by governments and projects and programs. ISGAN activities focus on five main areas: policy and standards and regulation, finance and business models, technological system development, workforce skills acknowledgement, and users and consumer engagement. ISGAN facilitates a dynamic sharing, technical assistance, peer review, and project coordination among its contracted party. ISGAN's value proposition lies on conferences and workshops, policy and technological briefs, discussions and technical papers, and casebooks and webinars as this one. So within the ISGAN, we have the virtual learning, which offers the ISGAN community means of rational and continuous technical skills to update in the field of smart grids. And the virtual learning is proposed as a set of e-learning and reading core modules dealing with the entire value chain in the electricity sector. So just to give a little bit of the introduction of the webinar today, again, revolutionizing renewable energy, exploring the biomass-fired top cycle BTC plant. This webinar is a collaboration of the EU-funded Bio-Flex project and offers a unique opportunity to uncover the future sustainable energy generation. It focuses on renewable energy generation alongside with the Phoenix BioPower, who is a company that is a pioneer on biomass-fired top cycle BTC plant. The innovative of this plan shows the high efficiency and flexible integration of biomass and renewable hydrogen, delivering a cost-effective solution combining heat and power generation within the energy system. Discover how this cost-cutting engine optimizes the source, utilizing and contributing to renewable energy adoption at a global scale. The speakers of today are Henrik Bage, the CEO of Phoenix BioPower, a co-founding partner of Phoenix BioPower, and Michael Bartlett, who is a CTO and founding also of Phoenix BioPower. During the webinar, feel free to use anytime the Q&A tool to pose any questions, and the speaker will answer at the end of the presentation. And the webinar recording will be available also in ISGAN YouTube channel. Now I give the floor to the speaker. Enjoy the webinar and the round table that will come later. Thank you.
As Juan Pablo said, my name is Henrik, CEO of Phoenix BioPower, and we are today in Europe and the world as a whole. We're in the energy transition. Okay, the energy transition is primarily about electrification. And I'm taking here Sweden as an example, and the picture is pretty similar across Europe, especially, where basically Sweden today produces around 160, 180 terawatt hours of electricity. We export a little bit and consume the rest. And by 2040, we're supposed to be net zero. Okay, the thing is, in Sweden, or the Energy Sweden have calculated that Sweden needs to be producing something in the ballpark of 300 terawatt hours of electricity by 2045. But out of the existing fleet, only 40 will remain. So that means we need to add about 290 terawatt hours worth of production by then. That's 21 years from today, people. So that means we need to basically double the product. We need to add twice of what we consume today in 21 years. And if we want to take that into some sort of manageable terms, so one extreme would to build 31 gigawatt nuclear reactors to match this need, or 20,000 onshore wind turbines. This is just, it's not going to happen. These are the two extremes, just to give you a mental picture of the challenge that we meet. We think that the future is a mix of everything. And our part of the answer is high efficiency biopower, which is on demand, so you can respond to the need that varies across seasons, but also as short as intraday. It's scalable from somewhat small size of 10 megawatts to beyond 100 megawatt electric per unit. And this will then enable a massive climate impact on the through implementation of our technology. So how do we do this? Traditional steam biopower is basically a steam engine. You take your fuel, you burn it in a boiler, generate steam to drive a turbine, and you get roughly around 30% electrical conversion from the energy in the fuel to electricity. The rest is heat. What we do, we take the same fuel, but rather than burning it in a boiler, we put it in a pressurized gasification system, whereby we heat up the fuel to around 900 degrees with very little oxygen. That means the solid biomass is then converted into gas, which we clean up. We add steam into the process, and then now I have a clean syngas, which I use to drive a gas turbine. So we're not using a steam turbine, we're using a gas turbine for the burning. And that one in turn drives the generator. This is a more efficient thermodynamic cycle whereby we produce more electricity. At the back end of the gas turbine, we have a steam generator, which generates the steam that I use in my system. And the steam also works as a heat carrier to carry over the thermal energy from the gasification to be recycled in the gas turbine. And at the back end, I now have a flue gas, which contains a lot of water in the form of steam, which I want to recycle. And I use that through a flue gas condenser, giving me a heat stream, which I can use for space heating, or I can, together with a heat pump, use it to drive the reboiler of a carbon capture unit. And that gives us a very high electrical efficiency, both for combined heat and power or for BECCS applications with negative emissions. So on the high end, so we get a lot more electricity from the biomass compared to your traditional technologies. We can get, in a district heating setting, we can get over 3 times more electricity generated from a given district heating grid, which is very important together with the energy transition, because not only do we need to produce more, but we also need to produce more locally. So we reduce the need for transfer capacity, because building power lines is, 1, expensive, 2, takes a lot of time, and in many areas not very popular. And also this together also drives down the production cost of electricity in form of the lower levelized cost for energy produced. This technology for many people sounds like a very narrow Nordic-based kind of thing, because yeah, we have a lot of forests here in Sweden, as you can see here behind me. But this is actually a very, very big market, because we're not targeting just forest residues. We're also targeting agricultural waste streams. So that means basically wherever you have farmland, you have waste streams, and there is a market for us where there's fuel. So we see that the serviceable obtainable market in the short term is €1 billion market. And the bioenergy market grows 3 to 4 times more than the global economic growth per year. So this is really a growth market that we're targeting. within the space of our technology platform, we can then address certain different market areas. One I've mentioned is the biopower and heat, or the CHP market, and also the negative emissions biopower with BECCS. But we can also split apart our plant technology into two main subsystems, the gasification and the gas turbine, where the gasification system can be used to utilize biomass waste streams to produce industrial feedstocks in terms of green gases for industries, like hydrogen or syngas that can be used for methanization process in the chemistry industry, or you can use it as a burner gas. The other part is to use the gas turbine as a peak power and a system, grid services unit that can operate on any gaseous fuel, including hydrogen with ultra-low NOx emissions. We as a company, we develop technologies. Our role is to be a technology developer and provide key know-how and IP within the space of gasification, combustion, and plant. And our business model is based on cooperating with partners like EPC and gas turbine OEMs to provide a turnkey solution to the end user. We are a small team now. We're about 12 people, primarily located in Sweden. We have a high academic profile with several PhDs and a professor. And also we have a broad experience from notable companies from industry, both within renewables, but also in heavy industry. And we've invested quite a few man years in our careers, but also in the technology development. And with that, we'll see if we can show a little film, and then I'll be handing over to my colleague, Michael. So this is basically an illustration of what our smallest plant, the BTC, we call it the P10, which is a 10 megawatt plant. I don't know if the film keeps stopping. I don't know why. Anyway, what you see here to the left, the tower is the gasification tower, and the small house next to the tower is the machine hall, which houses the gas turbine. In the middle, we have the fuel yard, and at the back end, we have the fuel treatment plant for where we dry the fuel, and we also pelletize it to make it homogeneous into the process. This is what we need. That's primarily for the smaller units. We do not foresee that we need the pelletization for the larger units or plants. The total footprint of this plant is somewhere between 2 and 3 football fields that you can imagine, looking at the sizes of the vehicles. And it's basically this is just an illustration where how big it can be. This site can easily be expanded with another unit. You can consider you put it on the parking lot, and you expand just a little bit with a little bit of fuel yard. The fuel treatment plant will basically be about the same size, and then you thereby double the size. So you have pretty high marginal efficiency on footprint for a second unit. We can also add then BECCS capabilities, etc., onto this plant, which is sort of the same size as the plant in itself, the gasification and machine hall for the turbine. And with that, I hand over to Michael.
So I'll just turn my mic on, and then I'll take control. There we are. So as Henrik has presented, we're developing our first unit there, which is the P10. But we foresee 3 standardized units for the market, and this really is because unlike steam turbines, gas turbines, you only have a certain number of models to cover a broad market. So it's too expensive a machinery to develop for individual purposes. So you have to produce standardized units. It also helps you standardize the engineering around the gasification and the fuel treatment, which brings down costs. So we believe in 3 sizes to cover the market: 10 megawatts electric, 40 megawatts electric, and 100 megawatts electric. And of course, as we scale up, we get better efficiencies and lower costs for these plants. Initially, we target, of course, forest residues, which are the say, most common plants fuel in the Nordics for CHP plants. However, we do see over time expanding the fuel flexibility towards agricultural residues, in particular going via bagasse, which is a very suitable fuel, corn stover, and then before going to more low quality and difficult fuels like straw. The gas turbine itself can utilize, as Henrik has presented, hydrogen, natural gas, but we see a very good fuel flexibility, which we'll come to in the project, where we can utilize hydrogen, natural gas, even methanol, even in the future liquid fuels. The main, of course, driver of our technology is the efficiency increase. And if we plot here basically the entire Swedish fleet of CHP plants across scale, so if this is the fuel input to the plant and this is the electrical efficiency, we can see that there's quite a large leap in efficiency across the scale. Of course, there's a scatter of what conventional plants reach, depending on the fuel, depending on the site-specific aspects and the economics of that particular application. So, but we can see here that the range of, let's say, the launch capability and the mature capability of where we see it can go is a significant jump. So we usually say about 50 to 80% above the conventional plants. And that's driven by basic thermodynamics. We change from a steam cycle to a gas turbine system. That's number one. So you get a higher temperature in which to drive the conversion efficiencies, your Carnot efficiency. The second thing is that we recover all the heat from the gasification system in a very, I would say, elegant way. We inject steam into the gas cooler, thereby superheating the steam and cooling the gases at the same time, which are the two functions you need. And so that brings all the energy to the gas turbine. And then the third is that we use only waste heat at 70 degrees to dry the fuel, compared to other gasification systems where they use live steam, for example. So these three things combine to give us a large efficiency increase compared to the conventional systems. If we look at also applications where we have negative emissions, we've seen, of course, across the IPCC scenarios, but also the International Energy Agency, that carbon dioxide removals are core to reaching net zero and to even, let's say, compensating for an overshoot. With biomass, we have a unique situation where we can utilize waste streams of biomass, bringing in the CO2 from the carbon, let's say, that the trees have absorbed, and capture that and sequester it. And at the same time, we provide services such as electricity production and heat production. So this is a large difference towards direct air capture, where you're just consuming energy to do carbon dioxide removals. Here we are producing useful products for the market while doing carbon dioxide removals. That, of course, is not unique to the BTC. So if you compare it to conventional plants with a steam turbine, we have studied this quite deeply and seen that we have a consistent improvement of about 60% more electricity per ton of negative emissions that you generate. So that represents this 60% increase from a conventional plant to our BTC. And that drives also economics. And across all of this is why we try to go to higher efficiencies, because it decreases fuel costs. And it also decreases specific capex, because if you have per megawatt hour of electric produced, you have more capex if you have a steam cycle, because there's less electricity. So these things drive us towards actually cases where you have negative marginal operating costs, and a plant, therefore, that would stay in operations throughout a year. If we look at CHP without any CDRs or CO2 capture, we would, of course, utilize the waste heat, which here is driving the CO2 capture for district heating. And as Henrik's already talked about, there can be 3 times more local renewable energy in that case. And the marginal efficiency, you have to, of course, add more biomass to the system to get that additional electricity. But the marginal let's say, efficiency of that additional biomass addition is from 70 to 100%. So in other words, if today you have a system that looks like this with 40 megawatts of fuel coming in, producing 30 megawatts of heat and 10 megawatts of electricity, for that same 30 megawatts of electricity, you produce 30 of heat, sorry, you produce 30 megawatts of electricity. The additional fuel was 25. So you're producing 20 megawatts more electricity with 25 megawatts of additional fuel. So that is the marginal efficiency of increasing the ratio of heat to power. And that is a very large, I think, when people talk about what should we do with biomass, this is an extremely efficient use of biomass. You get up to 100% electricity from that biomass. Of course, that in itself will not drive the installation of these plants, and you have to have economics with you. So what we see also is that there's up to a 30 euro per megawatt hour lower cost of heat if you're looking at electricity prices of around 70. So that's the let's say a little bit of an overview of the use cases of how this technology will fit into the energy system. Now, importantly, is how do we get there? And we have a scaling roadmap where we see that we want to install the first P10 unit by 2030. And working back from that, we need to start working on, of course, the EPC and the demonstration plant today. It goes via a basic scaling up technology where we go in the first phase, we build the gasification system at full scale, but we operate at reduced pressure and power with a rebuilt gas turbine. This is to make sure that we have, whoops, that was not meant to happen. To make sure that we have reduction of risk before going to the full scale plant with a brand new gas turbine. So we demonstrate here that the BTC technology works. We demonstrate the gasification system integrated with the gas turbine. And then before we go up in pressure, in power, and with a new gas turbine to achieve the full 11 megawatts of electricity. So that is a brief overview of Phoenix BioPower and our, let's say, technology of the BTC. Now I'd like to step into the Bio-FlexGen project, which is a great project we're conducting together with many partners within the EU, with the purpose basically to increase the cost effectiveness and flexibility of biomass-fired CHP plants. And we have here, as you can see, partners across the spectrum from technology owners like Phoenix BioPower, through research institutes, universities, utilities, LCA experts, etc. And it's covering, I think, 3.5 years project and 6 million euros in budget. The basic concept is the BTC that we've just outlined. We're looking at the products of electricity, heat. But the big difference in this is that we've brought in the vector of hydrogen to see what kind of flexibility benefits we can get from adding that energy vector into the system. And of course, CO2 as a negative emissions option. We're looking at feedstocks, woody residues, but with very high ash content. And we're looking at how we can utilize the gas turbine as a fast response unit with hydrogen as a fuel. So again, just to recap, the BTC technology is being examined with a broad spectrum of products, not just electricity, heat, but also hydrogen and CO2. We're looking at different types of feedstocks, and we're looking at how to start the gas turbine and run it with hydrogen, which is a very challenging fuel. So the goal as such is to develop that concept. The central technology is for that concept to TRL4. And so that includes the gasification system in a technology which is called the hybrid fluidized bed reactor. And also looking at the combustion, because if you're going to run on syngas and you're going to run on hydrogen, these are two very different fuels with very different combustion properties. So how do we do that in our combustion system? And then we need to evaluate, if we've got 4 products, how do those 4 products work together? What is the, let's say, integration into the energy system, and how do we get the most out of this flexibility? So it's not just Phoenix who's doing it, as I said before, it's a great group of people. So here we are in Madrid. So a big credit, first of all, to everyone who's contributed here. It's not just us at Phoenix. So I'd like to just give a brief background of why this project is needed. And I mean, the volatility of prices, I think we all understand that now. In 2021, 2020, when we wrote the the proposal volatility wasn't that high comparatively. It was coming, and everyone knew it was going to be a challenging energy system in the future. But I don't think anyone saw this of course, volatility coming, which was caused by the Ukrainian war, but also supply chain issues, and then in the end, the deeper and deeper penetration of variable renewables. This situation, of course, is something that challenges the profitability of CHP plants, in the need for flexibility, the costs of that flexibility, and the need to adapt to situations where prices can be 0 or prices can be 150. Responses to those price signals need to be quite fast, and it needs to also extend beyond seasons, which is the heating season for a CHP. So as you can see with a CHP plant, this is the total demand of heat over a year, but typically the base load is filled by waste heat or some sort of very low cost supply of heat, and the CHP plants run a limited amount of hours per year, maybe 50%. And so there are several challenges here that we're trying to meet. One is that how do you efficiently use the capex that you've deployed during this period of year where there's no demand for heat? How do you make the plant competitive and give products to the market which motivate operations? And how do you, what is the technology required for that? So we came up with 3 basically operating modes to meet those challenges. The first mode is to run the plant as a CHP, which is what it's meant to do, produce heat and power with very high yields of electricity. And that, of course, stabilizes the system, allows more penetration of variable renewables because you have stable local production and transmission capacities are no longer limiting. The second mode during the summer season is to switch from producing power and heat to producing hydrogen and CO2. And this is basically utilizing that same gasification system we talked about earlier, but instead of sending the syngas to a gas turbine, you send that same syngas to a hydrogen production unit. And that hydrogen production unit, basically what it does is shifts the CO content to hydrogen, removes the CO2 then that is generated, and then purifies the hydrogen. So you have 3 steps in that, main steps in turning syngas into a high quality stream of hydrogen. And the idea here is, of course, is that the hydrogen can be used by industry and brings value then to the plant, thereby allowing the operations. The third mode is that while you're doing this gasification, of course, the gas turbine is idle or is offline. So how do you operate it if there are needs to support the system? And the future is perhaps not a fossil-based fuel like a natural gas or oil, but instead is something like hydrogen. So that's the third mode of operation, is that you transform hydrogen from the grid into electricity when the prices motivate that and when the grid requires that. So these are 3 modes that we've been examining in BioFlexGen. Conventional CHP operations producing hydrogen and biogenic CO2 during the summer season. And then the third mode is producing power from hydrogen during the summer season when prices demand it. So the 3 main technologies then that are required to do this are as follows. So I'll give you a brief outline, and then actually we have a second webinar where we'll go into the details of each of these technologies and present the results of how far we've come. So the first technology we have is the gasification. So as we outlined earlier, the gasification system takes raw biomass, combines it with some oxygen from air, and heats it up in a fluidized bed where it converts into syngas. So syngas is a combination of hydrogen, CO, methane, CO2, and contaminants like tar. So the gasification system in the BTC has to operate at high pressures to be able to operate with the gas turbine efficiently. And if we now add on the requirement to operate during the summer times, it has to be able to switch from oxygen-blown operations when it's producing hydrogen to air-blown operations when it's producing power. And this capability is not trivial. It means that you have to manage quite different velocities and airflows in the reactor, and we have to manage the, let's say, the temperature profiles in the bed in the oxygen blown case. So that is the main focus of our technology development, is how do we operate at high pressures? How do we swing between oxygen and air blown operations? And how do we utilize that across the different loads that are required for the gas turbine? And when we were operating, we started the concept, let's say the project, with a concept of this gasification system. We have so far developed and built a test rig for cold conditions with a 5 megawatt scale reactor. We're also testing at pressures of 15 bar in a fluidized bed to test out the oxygen blown operations and air blown operations with these low cost feedstocks. So those are the two main activities we're doing in gasification. And of course, we do modeling to support that. The second area is combustion. So when we talk about, before we talked about combusting syngas, which is a very weak fuel, we also dilute it with steam, so it becomes even weaker. And then we talk about utilizing hydrogen, which is the other end of the spectrum, the most reactive fuel you can find. Those two must be utilized in the same system with high stability. You don't want to lose the flame at pressure in the middle of operations, and with low emissions. So that is the real novel requirements here for this combustion system. And what we see is that we've developed what we call the PAX combustion system, where we dilute the fuel, the hydrogen in this case, with steam, or the syngas with steam. And we have what is called mild combustion, which is with very low levels of oxygen in the system and very even temperatures throughout. And this promotes very nice fuel flexibility, and it promotes low emissions. And this is what we've developed in the project, from basic concepts through testing at pressurized systems with pure fuels, hydrogen and natural gas, and now also with syngas at our rigs from biomass. And then the last step will be to take this burner system to pressure in rigs in Berlin. And the third area is the plant. How do these things fit together? Of course, I've outlined 3 operating roads, so we've gone through those and simulated them and looked at the performance. And then beyond that, how do you integrate that into the energy system? So Comillas and others have looked at how do we operate a BTC plant in Sweden, how do we operate in Spain with different use cases, with district heating or industrial waste, steam requirements. How do they dispatch into the system and in both today, and they'll also be looking at 2040, 2050 as scenarios. So those are very interesting studies that we're just getting into. So this was a run through of the BTC in general, Phoenix BioPower as a company, and a very high level on the BioFlexGen project. We'd love to tell you all about the achievements so far. However, there's just too much to go through. So what we're doing is a cliffhanger now. So we will detail that out in the next webinar. However, we have very good results where we're seeing the gasification system, the concept is being proven out at the 5 megawatt scale cold rig and the fluidized hot rig. And we're also seeing that the burner and combustion system development is going very well, giving very low emissions and good stability across the fuels. So we'd love to invite you all to the next webinar. We'll go to those in more detail. And of course, if you have questions now, we'll be happy to answer them.
Mm-hmm. Thank you, Mike. Yeah, indeed, we got very interesting questions. If you want, I can read them and then you answer. So the first one is, well, thank you for the excellent presentation. I'm curious whether converting biomass into electricity might be underutilizing its potential. Wouldn't it be more effective to convert biomass into liquid fuels, which is thermodynamically more efficient and high-value product?
Mm-hmm.
What do you think?
Yeah, I mean, this basically comes to a slide, which is this. I mean, what do we do to get the most out of this pile of sticks and residues and wood? And understand the question very well, but if we look at, of course, there will be a need for liquid fuels. So don't get the next slide wrong. But if you look at transportation, the most efficient thing you can do is electrify transportation. And if you use electricity, let's say here from, how do I get the animations working? No. So
Yeah.
If we look at, for example, if we were to take it, just say we have a terawatt hour of biomass, and we want to convert that into, let's call it natural gas, 60% efficient, roughly, and that will give you out to the wheels of the car maybe a 0.1 terawatt hours of propulsion. And you get rid of some petrol, which saves you 135,000 tons per year. So that's nice. And we all need mobility, and that's important. But if we think about the wave of electrification and electric cars, if we were to take that same terawatt hour of biomass and you convert half of it to electricity, which is our basic goal, and you distribute that out to cars, you get 4 times more the distance in those cars, and you get then 4 times more avoidance of CO2. This is a very basic, of course, example, and there are more complexities to the system than this. But I think the best things we can do with biomass is actually to help electrify things. And wind and solar will do bulk lifting, but you need to have stable systems. You need to have local production, which helps transmission. You need to have security of supply, which biomass gives you if you're using residues. So I think there's of course will be economics behind this, driving things. This is a more system thought. But if perhaps sustainable aviation fuels is of course a difficult one to electrify. So there you could talk about things, but is it better to go through Fischer-Tropsch, which is a very inefficient process, and put that into an airplane, or is it better to offset airplanes through doing CO2 capture and sequestration? So there are no easy answers to that question, but we see that we can do electrification and CO2 capture very well. So that's what we focus on. Other people can focus on Fischer-Tropsch and sustainable aviation fuel, and good luck to them.
Thank you.
Added to that is also the fact that, okay, what do you want? What kind of energy do you need, and what kind of atoms and molecules are you looking for? I mean, this is the example of, as Mike been talking about, is transportation and mobility. But you also have, for instance, the chemical industry or the other industries that needs these hydrocarbon for industrial purposes to phase out fossil, and then converting into methanol might be more efficient.
Yeah, just to add,
especially if you want to move the energy from one place to another physically.
Yeah, an additional benefit, I would say, from the biomass, of course, is that that you can store it as well. Like it's not the gas, as Mike, as you said, now for wind and solar, is storage is still expensive, but if you can store the feedstock and produce when complement these other renewables, then you will get better system.
And it's not too expensive to store a big pile of trees. That's or residues. Yeah.
So another question from Jaime Guerrero. How do you deal with tar? Do you directly burn the gas without cleaning it? And how much biochar do you produce? What do you do with it?
Good question. So our concept is one of hot gas cleaning, as it's called, which means that we keep the entire cleanup system above the tar condensation point. And that means we take the tars into the combustion system where they directly burned. So we clean the gases by basically we bring the gas under the ash melting point and sublimation point. That's what the gas cooler does. We bring it down from 850 down to about 500 degrees Celsius. Maybe I can bring up a flow sheet here. Well, maybe one you've seen, so you don't get to. So here on the gas cooler, we come down from 900, well, from 850 degrees coming out of the gasifier cyclone down to about 400 to 500 degrees Celsius there. And that's where the fly ash, or more importantly, the alkali metals sublimate onto the fly ash and other inorganics. And then we capture that in a very high efficiency filter that operates at high temperatures above 400 degrees Celsius. Of course, the risk is that there can be tar bridging and there can be fouling here. And that's one of the key operating, let's say, know-hows as to how to operate this system with high reliability. But that means that we get tars into the syngas and we get that into our combustion system. And there we see we have a very good performance with the atmospheric tests that we've done on converting that cleanly to CO2 without any CO or particle emissions.
Yeah, indeed. Also, Rolf asked exactly that. How is the cleaning done to remove the tar? So I think also you answered that question.
Yeah,
already.
and as to biochar, when we're using woody residues, we see that we convert as much of it as we can to syngas. That's our target, is to have efficiencies above 97% in the gasifier. That means 3% is biochar somewhere, roughly. And that stream is in basically ends up in the bottom ash, the fly ash here of the filter, and that needs to be taken care of in the second step. The bottom ash from the gasifier is actually quite much like from a boiler. You have very low levels of carbon in it. When we go to agriculture residues, then we have a concept that we're developing in another project where we will operate the gasifier at lower temperatures, and there will be biochar production in the bottom coming out of the cyclone, basically. So there we have a concept of how to separate out the biochar from the bed, and the amount of biochar in that case is somewhere around 10-15%, let's say.
Right. Thank you, Mike. There is another very interesting question, I think, in the project. By the way, I'm also working in the BioFlex project, but we will need to address that is, if Top Cycle is so promising, why is not done already? It is not rocket science, but just a new combination of existing technologies. However, increasing complexity, of course, or what are the issues? High capital costs only, or technical challenges, or any other? What do you think are yeah?
I mean,
what do you think?
Towards commercialization, that's a good question. Top Cycle, I mean, as it's in inverted commas there, just combination of existing technologies. I'd say the gasification system which we're developing is for pressures which have never been done commercially. Very little gasification has been done, of biomass has been done commercially at pressure. Most of it is atmospheric, so that's one novelty which people are concerned about. So you need to show that that is feasible, reliable, and cost effective. So that's one challenge, is high pressure gasification. So I wouldn't say just existing technologies. In the gas turbine, you have the combustion. Nobody has done, let's say, stoichiometric combustion in a gas turbine with this amount of steam. So that's also new technology. I would say the barriers to commercialization, however, lie in the total development cost, and people are unsure when we talk to investors, I think, about the role of biopower in the future energy system. I think people are unsure if it's I mean, we showed a nice graph where biopower becomes a very large part of the energy system, and that's a scenario from the IEA, and we know that biopower is growing at 10% roughly per year. But investors work in groups, I would say. I don't want to use herd mentality as a word, but in groups. And the solar and wind and battery is the focus, and hydrogen has a huge buzz around it. But biomass is, in particular, biopower is unknown for investors in terms of venture capital and those people we need to get beyond the TRL 4 or 5. So that is a challenge, actually, in terms of talking about biomass, talking about sustainable use of biomass, and then talking about biopower. So there's a lot of complexities in there. So I think one challenge has been absolutely to find venture capitalists who have the mindset around biomass and biopower that matches our vision. High capital costs for the first plant, certainly it's a high risk thing to put these things together and make the first plant. So to make that scale up process I showed you, this is a 1 billion euro project roughly. Sorry, 1 billion crown, 100 million euro project. So that is, of course, a large amount of money that we need to mobilize. Henrik, do you have any further comments on that?
No, not really. I mean, there's, especially around the biomass, the feedstock, there's been a lot of discussion, especially outside of the Nordics, of whether to use virgin biomass for energy and whether that is sustainable or not. With the new RED3 in Europe, the cascade principle will be implemented. So we all know what a plank looks like, and we also know what a tree looks like. They're kind of not the same. So first you do your lumber for planks and your boards, and then you take high value parts of the tree to make pulp and paper. And then you go to fibers and chemicals. But you will still have about 20-25% of the biomass in a tree that you cannot use higher value products of. That is today used as energy throughout the Nordics in our CHP and heat plants for district heating. Now we've kind of luckily last year we educated the rest of Europe. This is how you do sustainable forest management and usage of the biomass. And with the new RD3, the threat against biomass as an energy source has sort of been handled and accepted, because there are very different views of how to manage forests in, say, Benelux than Sweden. Because we're basically, I think, 60-70% of Sweden is covered with forests. So we have quite a few spruces and pines. So I think that's one hurdle we've been facing in terms of the funding and the development and sourcing venture capital for this development effort is the ambiguity around biomass as a renewable energy source.
Thank you. Very good. Yeah, it's really under the discussion currently, how to manage woods and yeah.
And I mean, what's also interesting, you can see, I mean, the forestry industry is, of course, generates a large stream of residues, which certain countries have mobilized, other countries have not. And then there's also, I mean, not to forget, there's a large streams of processed residues from agriculture. I mean, it's so of course a lot of that can be filed down again, and a lot of it can be used feedstock for animals. But in general, I think there's an interesting topic to be had around. I mean, 70% of growing stuff goes to animal feedstock. It's the most inefficient way to feed ourselves we could possibly think of. So there's a lot of debate around using biomass as energy when we should be using it for feedstock. The conflict is that we're using it for animal feedstock, not for people feedstock. There's of course a large debate around that. I saw a question there about.
Yeah, you can read it, Mike, if you.
Yeah.
The last one. It's like a comment, but yeah, if you want to comment on the comment, yeah, go ahead.
Was there a comment on the comment? I didn't see that. But the viability of hydrogen production from electrolyzed water as a strategy for achieving decarbonized goals is questionable without hydrogen, without liquid. Okay. Yeah, I see your point. I mean, hydrogen production from electrolyzed water. I mean, that's a broader system question, whether that should be done, and how much it should be done to feed. I mean, one is how to produce hydrogen, and then there's a question about where to use the hydrogen once you've produced it. And that's a very broad discussion. I'm not sure if I want to treat everything in that, but I would say using hydrogen for example, steel industry and other types of heavy industry that there's no other alternative. I think that's a good way to go. Using hydrogen in let's say heating of houses, I don't think that's a particularly efficient or smart way to go. But these are my opinions rather than there are a lot of people with different opinions on that.
Okay, thank you. I think we got a good discussion and we cover all the questions that were there. Thank you all the audience. I don't know if you want to say the last word. Maybe, I don't know, also Regina or Micah, if you want to share the information about upcoming webinar as a reminder, and from the anything you want to post on the chat or any link that maybe that could be useful.
Yeah, we're still discussing about the date, but this will certainly be in the first week of September. So just follow us on LinkedIn, on our channels, and well, stay tuned. And thanks for all the people who took part in it, and thanks for the lively discussion.
Thank you, Regina. By the way, Regina is well, Regina, please introduce yourself because we didn't have time. But it's
it's just my name is Regina Schwalt, and I'm responsible for the communication dissemination of Bio-FlexGen.
Mike, Henrik, any last words?
No, thanks for joining.
Like and subscribe, as they say on YouTube.
Yeah.
Okay, thank you. As a reminder, also the recording will be available online. Just last thing, also.